This video is going to start into the gases chapter. That's chapter 11 in the TRO textbook. And so there's probably going to be at least 2 videos on the chapter so that there's not too much in the single one. But the first one, we're going to try to get through the individual gas laws. And so the chapter is on gases. And so what I want to do to begin with is just review some properties of gases from earlier in the semester. So some things that you should know about gases is that they are compressible, meaning you can smush or apply pressure to the outside of a container and make the gas particles get closer together. They will diffuse or spread out to fill a container. They're low density. The particles are far apart. That's why they're compressible. You can mix them in any proportion. That's meaning you can make a mixture of gases. Say you wanted to mix neon gas and argon gas. You could make it 50% neon, 50% argon, or I could make it 80% neon, 20% argon. I can make it in whichever ratio I want. And that gases exert pressure. So I wanted to talk a little bit about pressure, and then we'll move into kinetic molecular theory for a second. So what exactly is pressure? Pressure by definition is force per unit area. And so pressure is equal to force divided by area. You could measure the force in pounds. And if this was in pounds and you put your area as a square inch, then you would have something called PSI, or pound per square inch. And you might have seen that unit for pressure, say in your car, if you were filling your tires, they're going to measure tire pressure in PSIs, or pounds per square inch. But there are many other units that you can see as well. Another unit you might see besides for PSI is something called millimeters of mercury, which is sometimes referred to as torr. And these come from looking at air pressure. And when you're looking at air pressure, you might measure that with something called a barometer. And if we looked at an open barometer, this is a very bad drawing of one, but say you had an open barometer, what you would have is some liquid mercury in here, and then what you have is a sealed tube sitting inside of here. And what's going to happen is the air around this is going to collide, air particles are going to collide with the liquid mercury and drive it, the liquid mercury up the tube. And so if you were at a high pressure situation, what would be true is the mercury level inside of the tube would be very high. And if you were at a lower air pressure scenario, the level would be lower. And so historically, in this very simplistic view of a barometer, they would measure the height of which the mercury rose, and they would measure in millimeters. And so the unit became millimeters of mercury. The person who developed a barometer is Torricelli, and his name is honored by using the unit of a torr. So 1 millimeter of mercury is sometimes referred to as a torr. More commonly, they're going to measure air pressure in atmospheres. And so there are so many different units of pressure that you could have. At standard atmospheric pressure, that's the pressure exerted due to the air above us. The unit would be 1 ATM, and ATM stands for the unit of atmospheres. And this is most common in science, not really common in everyday life. In everyday life, you would see PSI, and that's equivalent to 14.69 PSI, which is also equivalent to 29.92 inches of mercury, which you might see in weather forecasts, which is also equal to exactly 760 millimeters of mercury, which would be the same as 760 torr. And there's another unit called pascals as well, so you might see those, times 10 to the 5th, and pascals are common if you take physics. So most of the time in chemistry, we use atmosphere, PSI, or millimeters of mercury. Those are the three, and torr, because it's the same as a millimeter of mercury. But you might run into these other units, and you don't need to memorize those. You could always look them up, or they would be given to you. So what exactly creates this pressure? Well, if you had what creates pressure, if you have a sample of gas inside of a jar, that sample of gas is moving, and the gas particle is going to move around, and it's going to collide with the walls of the container. And those collisions create a force. And how many times they collide is going to be equal to involved in the pressure. If they collide more often, you're creating more force. Also, what area are they going to collide over? So you could take the surface area of the container as your area. And so the collisions are really created by the collisions of the particles with the walls of the container. Particles with the walls of the container. And so in the lab this week, you're going to see a simulator, which will go through and you can measure pressure, changing different variances, like what size are the particles or how fast are they moving, and all of those good things. So this leads us right into the next part of the explanation of gases. What I wanted to talk a little bit about is the kinetic molecular theory of gases. And the kinetic molecular theory is going to try to give explanations as to how gas particles exist, which will then lead us to why they behave the way they do. So I have 5 different pieces to talk about in the kinetic molecular theory. The first piece says that gas particles are moving rapidly and randomly in straight lines in a sample. So they're going to move in random directions, but they don't do spirals or curlicues or anything like that. They're just going to move until they collide with something. And when they collide with something, they can bounce off and move in another direction. Again, you're going to look at a simulator in lab this week. That will you'll be able to visually see that. When the particles are moving around, collisions occur. 2 types of collisions occur. Particles collide with each other, and particles collide with the walls of the container. In this is what creates pressure. In the collisions, what you assume that there is no loss of energy. Or momentum with the collisions. If you've taken physics, that will make a little bit more sense to you. Next piece of it is that the average kinetic energy is related to the Kelvin temperature. Well, this is true no matter what, not just for gases, but temperature measures average kinetic energy. And remember, kinetic energy from a long time ago is 1/2 the mass of the particles times the velocity squared. Remember, velocity really is speed with direction. So if a particle's at a higher temperature, they should be moving faster on average. If you're at a lower temperature, the particles should be going slower. So it's the first 3 going on. Kinetic molecular theory says that for gas particles, there are no attractive or repulsive forces between the particles. So the particles really move independent of each other. They're not attracted to each other and they're not repelled by one another. The last piece is that the particles are widely spaced. They're far apart from one another. So what we're going to say in this one is that the volume of the particles themselves is negligible compared to the volume of the container they occupy. Therefore, we're going to say that the volume of the gas is equal to the volume of the container. Now, that wouldn't necessarily always be true, but we're going to assume that's true. We're going to really work with what are called ideal gases. And ideal gases are gases that have all of the properties that I just described. You have all the described properties, and they follow the laws that we're going to follow, the gas laws that we're going to talk about next. In real life, not all gases act ideally, and when you go on to take Chem 1A, they'll start doing some corrections where things are not always acting ideal. But let me just give you one example. So we're making this assumption, right, that the volume of the gas is the volume of the container. That's because we're saying if that's the container, our gas particles are like this. So if you were to take the total volume of that container and subtract the little tiny volume of these 6 dots, basically you're still going to get the volume of the container. But if your gas particles were this big and that close, you couldn't make that assumption. You would have to say that the volume that is occupied by these 4 is so large compared to the volume contained here, you couldn't just ignore subtracting, right? You couldn't ignore the red to get the total amount of the volume. You'd have to subtract that out. Over here, these little tiny red specks are so small that we can just ignore that volume compared to the volume that is all of this. So this would be an ideal setup. This would be non-ideal. And here in this class, this video, we're only going to worry about ideal setups. So for the rest of this video, what I'm going to do is talk about some of the gas laws. And we're going to go through a few. You're going to look at Charles' law in more detail in lab this week. So here we go. Oops, let me get rid of that being purple. That's kind of a strange color. Let's look at the gas laws. So one of the first gas laws that we can look at is Gay-Lussac's law. And in this law, what it stated is the pressure exerted by a given amount of gas is directly related to the temperature at constant volume. So basically, mathematically, what it's saying is that pressure is proportional to temperature. And if I want to get away from proportional and I want to get to equality, I have to put in a constant, a proportionality constant. So basically what it's saying is pressure is equal to some constant times temperature. And then you could rearrange this and say that pressure divided by temperature is equal to some constant. And then what's really helpful about this law is what that means is if the pressure and temperature at one point in time is equal to this constant, then the pressure and temperature at some other point in time must also be equal to the constant. Constants don't change. Therefore, what you usually see as the mathematical version of Gay-Lussac's law is this. This will allow us to say, if you know the pressure and temperature at one time and you change one of those variables, you'll be able to predict what happens to the other one. Now notice this is at constant volume and constant amount of gas. The only thing that you're changing is pressure and temperature. So this kind of makes sense, because if you have a sample of gas and they're moving at a certain speed, they're going to collide with the walls of the container. Let's just say they're moving at 100 meters per second. If they're moving at 100 meters per second, there's going to be some number of collisions. If I raise the temperature, I'm going to increase the speed. And if I increase the speed to 150 meters per second, I'm going to get more collisions. If I get more collisions, I'm going to have higher pressure. So that is the rationale. And again, the lab this week is really great. There's a simulator online that I asked you to look at Charles' law, but you could actually look at Gay-Lussac's law in the same simulator, and you can see this actually in motion. So let me show you a problem we would do using this law. So the pressure of a sample of gas is 2.1 atmospheres at 295 Kelvin. Calculate the pressure if the temperature is decreased to 275 Kelvin. Notice we're always in Kelvin. For all of the calculations we're going to do, you want to be using temperature in Kelvin. There's a really good reason for that. If we look at the equation, we're dividing by temperature, and on Kelvin, we're never going to be negative and we're never going to be at 0. So these values for T1 and T2 will always be positive values. If you're in Celsius, temperature could be 0. You can't divide by 0, it's undefined, or it could be negative. And if only one of the temperatures is negative, then you would end up having to have a negative pressure, which is not a valid thing. So temperatures always have to be in Kelvin. If in a problem they're given to you in Celsius, you need to convert to Kelvin. Remember, to convert to Kelvin, Kelvin is equal to the temperature in Celsius plus 273.15. All right, so you're going to need this often in the problems. Okay, so now going through, in this problem, what's given to us? We have this information. We have a gas at 2.1 atmospheres. I'm going to call that P1. That's my original pressure. And we know it's at 295 Kelvin. I'm going to call that my original temperature. Now it's saying calculate what is the new pressure. So what is P2 if T2 goes to 275 Kelvin? So all you really need to do is plug into this equation and solve for P2. I like to rearrange first and then put values in. You can put values in and then rearrange. It's really algebra. That's fine. So I'm going to say P2 is equal to P1 over T1 times T2. I'm multiplying this side by T2 and I'm multiplying this side by T2. P2 is equal to P1 times T2 divided by T1. So then I could just plug in my values. P1 is 2.1 atmospheres. T2 is 275 Kelvin. T1, 295 Kelvin. Notice Kelvin will cancel. My unit will come out in atmospheres, and I'm going to get 2.3 atmospheres. Oh, I think I did something wrong here. I don't have my calculator. T2 is 275. This is not going to come out to be 2.3. I don't have my calculator. I'm very sorry. Please calculate that and I'll email you what you're going to get. How did I know it couldn't be 2.3? Because what happened in my problem is my temperature is decreasing. And so if my temperature is decreasing, then my pressure must also decrease. And 2.3 was not less than 2.1, so I knew something was wrong. So I apologize for not having the exact value, but if you could plug that through, that would be great. The other way you could have solved this problem is just knowing this relationship and not really using the equation. You could have done this as well. You could have said my original pressure is 2.1 atmospheres, and I know that it has to go down. I know the pressure must go down because the temperature went down, and they're directly related. So I could have just taken my original pressure and multiplied it by a ratio of temperatures, and I would have known I needed the smaller temperature on top so that this is less than 1. So therefore my pressure would go down. So I could have done it with rationalizing it versus doing the algebra, but of course you can do the algebra as well. So that one is Gay-Lussac's law. Again, it states that pressure and temperature are directly related. And the mathematical formula is P1 T1 is P2 T2. You would always be given 3 of these variables and asked to solve for the 4th. Next gas law we're going to look at is Charles' law. Charles' law states that the volume of a given amount of gas is directly related to the temperature of a gas at constant pressure. So does this make sense? If I have a container that's this big and those particles are moving around and they're going to hit the walls of the container, I'm going to create a pressure. I know from the previous law, if I increase the temperature, I'm going to increase the speed, and that would, or potentially would, increase the pressure. But Charles' law states that I have to be at constant pressure. So how can I make the pressure not go up? I have to make the volume bigger so that my collision rate is going to keep me at a constant pressure. So in order to keep constant pressure, the volume has to go up. So what that means is if temperature goes up, volume must also go up to keep pressure constant. So mathematically, this is going to look similar to the last one. It's going to say that volume is proportional to temperature. Volume is equal to some constant times temperature, and then we could go V over T is equal to that constant. And again, you could say volume and temperature at one point is going to be the same as volume and temperature at another point. The ratios must both equal the constant. Therefore, the mathematical formula that you're going to see for Charles' law typically looks like this. V1 over T1 is V2 over T2. Looks very much like Gay-Lussac's law. They're both direct relationships, so mathematically they're going to look similar. So here's a problem that you could use, that you could have to solve using Charles' law. What temperature is required to reduce the volume of a gas from 3.55 liters to 2.55 liters if it's originally at 35 degrees Celsius? What temperature is required to reduce the volume of a gas from 3.55 liters to 2.55 liter if it's originally at 35 degrees? First thing to think about is that the volume has to go down. If the volume has to go down, that means that the temperature has to also go down. This is because it's a direct relationship. So whatever I do, when I'm done, I should come up with an answer that is less than, my answer must be less than 35 degrees Celsius. This is a way you can check your work and make sure you're going well. Again, you have to always be in Kelvin, so I'm going to take my 35 degrees Celsius, I'm going to add 273.15, and going only to the whole number, that's going to give me 303 Kelvin. So I know V1, 3.55 liters. I know V2, 2.55 liters. I know T1 is 303 Kelvin, and T2 is what I'm looking for. I have 4 variables in my equation, 3 are given, 1 is my unknown. So what I need to do is solve for T2. So I have V1 over T1 is V2 over T2, and I want to solve for T2. Now this one's a little bit trickier because T2 is on the bottom. Do not solve for 1 over T2. I need to get temperature to the top of my equation. So I'm going to multiply this side by T2, and I'm going to get T2 canceled out. That means I have to multiply this side by T2. Now if I did my algebra correctly, I would have T2 V1 over T1 is equal to V2. But I want to solve for this. So now I need to multiply this side and this side by T1 over V1 so that these cancel. And my final equation is going to be T2 is V2 T1 over V1. So the algebra of that one is a little bit trickier to do, and you can verify that you do it right. I'll show you in a moment. But if we plug in our values in, V1 is 255 liters, T1 is 303 Kelvin, and V1 is 3.55 liters. And if you punch that into your calculator, I believe you get, I hope I did it right this time, 218 Kelvin. Now you could just left it in Kelvin because it doesn't specify in the problem, it just says what temp. However, if your only answers are given in Celsius, you might have to convert this back to Celsius. So you'd have 218 minus 273.15 to get back to Celsius. And you would have gotten minus 55 degrees Celsius. So if the question's open-ended, you could leave it in Kelvin unless it specifies it has to be in Celsius. Now, this problem looks like a lot of algebra, but you could have done that thinking about it a little differently. If you would have known that V1 is 3.55 liters, and you know that T1 is 303 Kelvin, V2 is 2.55 liters, instead of doing the algebra, you could have just rationalized what had to happen. I know that my volume is going down. Therefore, my temperature must go down. So I could have said start with my original temperature and multiply it by a ratio times a ratio of volumes. And so I could have said T2 has to be T1 times a ratio of the volumes. And if I know T2 has to get smaller, then this ratio has to be less than 1. And if that ratio is less than 1, it's going to be 2.55 liters over 3.55 liters, which is exactly what we had in the previous screen doing the algebra. And again, you're going to get 218 Kelvin. So if you're having trouble with the algebra, you could always backtrack and just use logic to solve it. The third gas law that we're going to talk about in this video is Boyle's law. Boyle's law states that the pressure of a given amount of gas is indirectly or inversely, if you like that word better, related to the volume of a gas at constant temperature. So this law is saying if you hold temperature constant, what happens to volume and pressure? And if you think about it, it's kind of easy. If you have a balloon filled with gas and I smush on it, squeeze it in my hands, I'm increasing the pressure. What's going to happen to the size of the balloon if I smush on it from the outside? The balloon's going to get smaller. So that is an indirect relationship. If pressure goes up, volume goes down. This is different than the previous. You could also say if pressure goes down, volume has to go up. The previous two laws were both direct relationships, and as one got bigger, the other variable increased as well. And again, you can play around with the simulator online for Boyle's law, and you can see this in action. So let's see what a problem for Boyle's law would look like. Here's a sample. Oh, I should do the mathematically first. So we know that pressure and volume are indirectly related. So what that means is pressure is proportional to 1 over the volume. And if I put a constant in there to make it equal, then I'm going to have to put volume on this side. So volume times pressure is equal to the constant. That means that volume and pressure at one point in time must be equal to volume and pressure at another point in time. Nobody writes volume first. When you look at Boyle's law, it's always going to be written P1 V1 is equal to P2 V2. And this is different. Remember, the other ones are P1 over T1 is P2 over T2. This is when you have a direct relationship. This is when you have an indirect. Right? They mathematically look different. So now let's do a problem for Boyle's law. A 4.50 liter sample of helium at 751 millimeters of mercury has the volume increased to 8.71 liters. What is the new pressure? So when we're starting out, you can write down everything that's given to you. We have a volume of 4.50 liters, and we have a pressure of 751 millimeters of mercury. These two exist at the same time, so I'm going to call them both P1. Those are at the same time. Saying the volume is going to increase, so my new volume is going to be 8.71 liter, and my question is, what is the new pressure? My formula, P1 V1, P2 V2. I know P1, I know V1, and I know V2, and I'm going to solve this for P2. Divide by V2. I'm going to have P2 is equal to P1 V1 over V2. Plug in all your values. P1, 751 millimeters of mercury. V1, 4.50 liters. V2, 8.71 liters. And liters will cancel. And if you plug that through, I believe you get 388 to 3 sig figs. And my unit will be millimeters of mercury. I could have had different units for pressure. Whatever units for pressure I put in is the unit for pressure I'm going to get out. Does our answer make sense? Well, what's happening to our volume? Our volume is increasing. And this is an indirect relationship. So as volume is increasing, pressure should be decreasing. So double check to make sure that your new pressure is actually less than your original pressure, and it is, so that is a valid answer. The last variable that you'll typically see in the gas laws is what happens to the amount of the gas. If you notice in all three of these, I always said at a given amount of gas. We didn't change how much gas we had in the sample. In the next segment, we'll talk about putting the amount of the gas changing, and then we'll get to some longer and more involved calculations involving more than changing two variables at any time.